strict divisors. Okay, so so today, first, I will try to introduce some detailed background and motivation in this project, and then we recall some previous results. After that, I will state our main results, the first part, and finally, then we give some key ideas for the proofs, and at last we ask some open questions. Okay, so today's talk is based on the joint work with Jie Liu, Wenhao Ou, Juanyong Wang, and Xiaokui Yang. Okay, so we start from projective variety X over the complex numbers C. And we say that a Q-Cartier divisor L is strictly F if it has positive intersection with every integral irreducible curve on X. And there are some examples for, so first, by the Nakai-Moishizen criterion, ample divisors are all strictly F. And the second, if X is a curve, then every strictly F divisor L on X is ample. And also, we consider the canonical divisor case. So if X delta is an L log canonical pair, in other words, this is a projective pair such that it has at worst log canonical singularities. And the log canonical divisor Kx plus delta is strictly F, then the abundance conjecture and the projection formula would imply this Kx plus delta is ample, because the abundance conjecture says that in this case, Kx plus delta is semi-ample, so it defines a fibration onto downstairs. And also, it is the pullback of an ample divisor from downstairs. Since it is strictly F, so it means that this fibration cannot contract any curves, so it should be a finite pullback of an ample divisor, so it is still ample. Okay, so in particular, if dimension X is no more than 3, then this Kx plus delta being strictly F forces our Kx plus delta to be ample.
Sorry, wait a minute.
Okay.
You mentioned in the first part of example A that you need not Nakai-Moishizen criterion to say ample divisors are strictly F.
Yeah.
Why?
I think this is a numerical criterion because the ample divisors all have the positive intersection with every ray in the Mori cone except for the 0.
I remember that this criterion is the criterion for a divisor to be ample, not ample to be strictly F, right?
But I think this is the if and only if, or
yeah, I mean, is the if and only if of divisor to be ample divisor using intersection with cycles, right? So
yeah,
nothing to do with strict F.
That is climb. I mean, this Nakai-Moishizen criterion means a divisor is ample if and only if for example, this D or L, the L power dimension Y times Y is positive for every subvariety Y.
Yeah.
If
so
and only so.
So
I mean, if this is an ample divisor, then by this numerical property, it has positive intersection with every irreducible curve.
I think this part no need Nakai. So ample divisor implies strict F is simply by definition of ample divisor. Pullback of ample divisor is ample, nothing to do with Nakai-Moishizen. I think. Yeah, this part has something.
Maybe maybe you are right. Yeah. Because the restriction, you can simply consider the
pullback ample is close immersion pullback.
Right.
Is finite pullback. Yeah.
So this is just the numerical property of the ample divisors, I think.
Yeah.
You are right. So okay, so let's continue. So the pullback of a strict F divisor along a finite morphism is still strict F. Also, the pullback of possibly non-ample divisor is still non-ample. So this property is just mentioned to say that if we can find a strict F but a non-ample divisor, then there are many such divisors. Okay. So the main question is, how far is a strict-left divisor from being ample? Okay, so this is our main question. So we know that the strict-left non-ample divisors do exist. This is first constructed by Mumford. So we let C be a smooth projective curve of genus greater than or equal to 2, okay, of general type. Then there exists a vector bundle E of rank 2 over C, such that the tautological bundle O1 on the projectivization PE is strict-left but not ample. In this case, the first chain class of E is 0, and by some calculation, we can show this O1 is strict-left but not ample. Okay, so the following conjecture is the initial point of this project. So this is Campana-Peter-Nels conjecture. So we consider a smooth projective variety X, and they conjecture that if minus K is strict-left, okay, if the anti-canonical divisor is strict-left, then X is final. In other words, the minus K is ample. Okay, so Serrano, okay, so we can see this is to study the property for the anti-canonical divisor. And to be more generalized, okay, Serrano proposed the generalized conjecture, or usually we call it Serrano's conjecture. And he predicts that the ampleness of a strict-left divisor after a suitable deformation in the direction of Kx. So usually we know a strict-left divisor may not be ample, but if we add a small multiple of this canonical divisor, then Serrano conjectures that it is ample. So let X be a smooth projective variety with a strict-left divisor Lx. Okay, so then Serrano's conjecture says that this Kx plus the sufficiently large T, TLX, is ample for sufficiently large T. Okay, I give some remarks on these two conjectures, the Campana-Peter-Nels conjecture and the Serrano's conjecture. So first, it is clear that the Serrano's conjecture for the case dimension X equal to N implies Campana-Peter-Nels conjecture for the case dimension X equal to N, because we just let this Lx be the anti-canonical divisor minus K. Okay, so Serrano's conjecture should be more general. Okay. And another thing, Serrano's conjecture for the case dimension X no more than N is important to the proof of Campana-Peter-Nels conjecture for the case dimension X equal to N plus 1. This is detected by Serrano. And recently, as observed by Haidong Liu, a positive answer to the log version of Serrano's conjecture in dimension 3 will give a positive answer to Campana-Peter-Nels conjecture in dimension 4. Note that here, this Campana-Peter-Nels conjecture is on the smooth case, but the log version of Serrano's conjecture in dimension 3 is for the is about the singular case. Okay, so the question is, what's the singular pair version of the Campana-Peter-Nels conjecture and the Serrano's conjecture? Okay, so we ask the following question. We call the singular version of Campana-Peter-Nels conjecture. So we consider a projective KOT pair X delta with the anti-log canonical divisor minus K plus delta being strict-left. And we want to know whether this minus K plus delta is ample or not. And the second question is the singular version of Serrano's conjecture. Okay, so similarly, we consider a projective KOT pair X delta and a strict-left Q divisor Lx on X. And we want to know whether this Kx plus delta plus the sufficient large multiple of this Lx is ample or not. Okay, so we note that the singular version of Serrano's conjecture has a positive answer on surfaces by studying the generalized pairs. Okay, so this is a joint work by Jin Junhan and Wenfei Liu in 2020. Okay, so they show that if X delta is a projective LC surface pair, which is more general than our KOT case, and with this Lx be a being a strict Cartier divisor. Then they show that this kx plus delta plus TLX is ample for every real number t greater than 3. Okay, so our main focus today is about the first question, and we shall study the Serrano's conjecture tomorrow. Okay. So today we will mainly focus on the singular version of Campana-Peter-Nels conjecture to study the anti-canonical case. Okay, so I will give some, we will record some positive answers on the Campana-Peter-Nels conjecture. So first, Maeda proved in 1993 that the surface case is true. Okay, so if X is a smooth projective surface, then this minus K being strict F is equivalent to this X being the pedal surface, which means this minus K is ample. And Serrano proved this conjecture for a smooth threefold in 1995. Okay, so a smooth projective threefold X with strict F minus K is final. Okay, so this result is very inspiring. And later on, Uehara generalized this result to the canonical threefold, means the projective threefold with only canonical singularities in 2000. Okay, so he showed that if X is a projective threefold with canonical singularities such that this minus K is strict F, then this minus K is ample. Okay, so Q final. And recently, Haidong Liu give some evidence for the positive answer on Campana-Peter-Nels conjecture in dimension 4. Okay, so he showed that a smooth projective fourfold X with this technical condition C1 square times C2 not vanishing, and minus K being strict F. Then he showed that this X is a final fourfold. But usually, the most difficult case is this vanishing case. Okay, there is another interesting project to classify such X with C1 square times C2 equal to 0. Okay, so this is another interesting project. So this is a partial answer on the Campana-Peter-Nels conjecture in dimension 4. Okay.
Sorry, I have a question. So
okay.
in Liu's theorem, he added this condition C1 square C2 non-zero. So if X is a final manifold, do we have such condition?
Not necessarily. In dimension 3, I think we can have such condition, but in dimension 4, there are some probabilities that this is 0. Yeah.
Are you familiar with the sketch idea of the proof of theorem? I mean the threefold case. Uehara, he considered singular canonical use minimum model program or something else.
Yeah, he runs some minimum model program, and he just he first reduced to the case the irregularity is 0. I think he gives some discussion first. The Albanese dimension, the irregularity is 1, is 2 or something. Then he excludes such possibilities. Okay. Then finally he reduced to the case Q equal to 0. Then he studies when excluding the such positive irregularities, he need to run the minimum model program. And finally, he reduced to the case Q equal to 0. And then he studies the étale fundamental group and to construct some contradictions. Yeah,
so is there any possibility for the strict F divisor with the arbitrary codal dimension, Ithaka dimension, like 0, strictly F divisor being
you mean the
codal dimension, Ithaka dimension negative? Is it possible?
Yeah, there is a possibility that this minus K has no section. Actually, we can show that if this minus K, once this minus K has a section, then we can show it is ample. at least on threefolds. Yeah.
So you need to find
Yeah.
at
So
least, okay.
yeah, usually at least on the threefolds, yeah, we can show that if this minus k has a section, then or somehow
even in surface case, it is hard to find a section for strict Neff divisor.
Yeah, I think so. Yeah, yeah. For general strict Neff divisor. If minus k, then in the surface case, it should have section.
Okay.
Yeah, because by the Maeda's theorem. Yeah.
Okay.
Okay. So Liu's theorem actually he reduced to the threefold case by using this non-vanishing condition. He reduced to the threefold case, I think. Yeah. Okay. So let's continue. So now there is an important theorem for us to study the singular version of Campana-Peter-Nels conjecture, which we call the structural theorem of KLT x delta with Neff minus k plus delta. Here we only consider Neff case. Okay, so this is a joint work by Juan Wang and Matsumura. But before that, we first recall some previous results. Okay, so first by the BDPP, if minus k plus delta is strict Neff, then we can show that this x is uniruled. Okay, and then another thing is about the maximum rationally connected fibration for the projective variety X. Okay, so for a projective variety X, there is a dominant rational map X to Y, which is unique up to birational equivalence, such that the general fiber is rationally connected and Y is not uniruled. Okay, so we say this map the MRC fibration of X. Okay. So recall that we say a variety is uniruled if it is covered by rational curves, and we say a variety is rationally connected if any two general points can be connected by a rational curve. Okay. So based on Mori, Span, and Brick, Kola, Miyaka, and Mori in 1992 and Campana in 1992 independently show that the final manifolds are rationally connected. And later on, Zhang in 2006 and Haken-McConnell in 2007, they generalized the rational connectedness of final manifolds to varieties of weak phenotype. In other words, a pair X delta with the Neff and big minus K plus delta. Okay. So this is the minus K plus delta being ample or Neff and big case. And we consider another building block, which is the Calabi-Yau manifolds. This is the for the K. This is not strict sense not in the strict sense. Okay, just the K trivial. Okay, so Bouville-Bogomol of decomposition claim that the Calabi-Yau manifolds are decomposed up to a finite tau cover into the product of abelian varieties, strict Calabi-Yau manifolds, and hyperkähler manifolds. Okay. And later on, by a series of works by Grab, Capex, Peter-Nel, Jewel, Hurin, Peter-Nel, Grab, Gunancia, Capex, and Campana, Paul, and Campana by the series joint works, and they generalize the Bouville-Bogomol of decomposition to singular KLT Calabi-Yau varieties. And later on, Baker, Gunancia, Lan in 2021, last year, okay, they dealt with the decomposition for non-projective K-trivial compact Kähler varieties. And also there are some progress in positive characteristics, but more technical conditions are imposed, okay, by the series works. And so now we back to our characteristic zero. The two important papers by Junyan Cao in 2016 and Junyan Cao and Andreas Hurin in 2017. Okay, they show that the smooth projective varieties with Neff anti-canonical divisors are constructed by rational connected manifolds and Calabi-Yau manifolds. Actually, they show that there is a holomorphic MRC fibration onto downstairs onto a Calabi-Yau manifolds with the general fiber being rationally connected. Okay, so inspired by these two works, the recent works by Junyong Wang in 2020 and the joint works by Matsumura Wang last year, okay, they constructed the structural theorem of a projective KOT pair X delta with NF minus K plus delta. Note that although these two joint works are inspired by the previous works Cao and Cao Huring, but the singular case is much more complicated, and there are many new tools to be introduced. Okay, so today, before we state our main results, let's review their results. Okay. So we start from a projective KOT pair X delta with the NF minus K plus delta. Then there exists a finite quasi-tau cover mu X prime to X, such that first, this X prime admits a holomorphic MRC fibration per psi from X prime to Y. Second, Y is a projective KOT variety with the canonical divisor being numerical trivial. So the last one, this per psi is locally constant with respect to the pair X prime delta prime. Okay, so let's explain what's the local constancy here mean. Okay, so this delta prime is just defined by the pullback along this quasi-tau cover, okay, from this X to X prime. And we say this per psi is locally constant with respect to the pair if it satisfies the three conditions. So first, for any small open set B, the inverse image is the product of B and a general fiber, F. And also, this holds for this boundary delta prime. And the second, every component of this delta prime is horizontal, dominant the downstate, not contracted by this per psi. And there is a representation rho from the fundamental group to the automorphism of the general fiber F, such that this delta F prime is stable under the action of this pi1 Y up to a scalar, I think. So that the base change of this X prime after we pass to the universal cover of Y, okay, splits into the Y universal times F, okay, splits into the product. And the downstairs X prime delta prime is the quotient of the upstairs by the fundamental group pi1 Y. Okay, so this means for the local constancy, the fundamental group of Y naturally acts on the fibers of this per psi. Okay, so I draw a picture for your convenience. So we can see, so with X delta replaced by its quasi-tau cover, so we still denote by this X. Okay, so we get a holomorphic locally constant MRC fibration from X to Y. We call it F. Okay, with Y being KOT and the canonical divisor being numerically trivial. And then we denote by this the universal cover, the projection map PY. And after the base change, this X times Y universal splits into the Y universal time the product, okay, of the Y universal cover and the fiber F. Okay, note that all the fibers of this fibration F are isomorphic. Okay, so the morphism F is locally trivial analytic fiber bundle with the fiber F. Okay, and every component delta I of delta is horizontal. And there is a representation rho from the fundamental group pi1 Y acts on this general fiber of F. Okay, every fiber of F. And a well-Q divisor delta F, which is invariant under the action of this fundamental group pi1 Y, so that this X delta is the quotient of the upstairs by the fundamental group via the diagonal action. Okay, note that this pi1 Y naturally acts on the F. So this is the structural theorem of the KOT pair X delta with NF minus K plus delta. Okay, so now let's state our main results. So before that, we ask a weak form of Campana-Peter-Nels conjecture. So let X delta be a projective KLT pair with the anti-log canonical divisor being stricken F. So the generalized form or generalized singular version of the Campana-Peter-Nels conjecture predicts that this is ample. But here, we only require, or we only want to know whether this X is rationally connected or not. Because we note that Fano manifolds or a weak Fano type are all rationally connected. Okay. So we can see the weak Fano type is rationally connected as proved by Qi Zhang in 2006. Okay. And when so our question is a weak form of the previous singular version of Campana-Peter-Nels conjecture. And when X is smooth and the boundary delta is 0, applying the inspiring results of the Cao and Cao Huring, Li Duo, Ou Wenhao, and Yang Xiaokui gave a positive answer to the above question in 2019. Okay, so this plants some evidence on the positive answer of Campana-Peter-Nels conjecture in any dimension. Okay, so they deal with the smooth case. And as a corollary, Li Ou Yang gave an analog of Morris result. So they show that a smooth projective variety with stricken F tangent bundle is a projective space. Okay. So inspired by the above joint works, our first main result is to give a positive answer to this weak form of Campana-Peter-Nels conjecture by applying the work, the joint work of Wang and Matsumura in 2021. Okay, so first, this is our first main result. So we start from a projective KLT pair X delta with stricken F minus K plus delta. Then we show that this X is rationally connected. And moreover, the augmented irregularity Q is 0. Okay, so note that this theorem A answers the weak form of a generalized log version of Campana-Peter-Nels conjecture. Here, this augmented irregularity is defined as the maximum of Q x tilde, where this x tilde to x runs over the finite quasi-tau covers of x. Okay. So this is you can also see the definition in the joint work by Nakayama and Zhang in 2010. And when this dimension equal to 3, I first proved it, okay, last year. And later on, we find that actually it holds in any dimension. And one can further generalize this theorem to the case when minus K plus delta is almost strictly F. Okay, so note that this is weaker than the stricken F. So this is defined by the pullback of a stricken F divisor from downstairs along a birational morphism. Okay, so in other words, we can show if this X delta is a projective KLT pair with almost stricken F minus K plus delta, then this X is also rationally connected. Okay, so our next main result will generalize this theorem A to the relative case and analyze such fibration like example B. Okay, so so let's recall that our example B is the projectivization of a rank 2 vector bundle over a curve of genus greater than 2. Okay. So this is our second result. So we consider a fibration from a normal projective variety X to a smooth projective variety Y. Okay, note that this smoothness is very important here. And suppose that this X delta is a KLT pair and the relative anti-log canonical divisor, which is defined by minus KX over Y plus delta. This is stricken F. Okay. So in our theorem A, our y is a single point. Okay. But here we require the downstairs is a smooth projective variety. Okay. Then we can show that this F is a locally constant fibration with rationally connected fibers. And the downstairs Y is a canonically polarized hyperbolic projective manifold. Okay, so recall that a projective manifold is said to be canonically polarized hyperbolic. So there are two definitions. The first is the canonically polarized if the canonical divisor is ample. Okay, and we say it is hyperbolic if every holomorphic map is constant from C to Y is constant. In other words, this Y does not contain any entire curves. And we note that the theorem B is a more general form of theorem A because we can just let this Y to be a single point, and then the fiber is just the whole X. Okay, so this X is rationally connected. However, this theorem A is our previous theorem A is one of the key ingredients during the proof of theorem B. So to show the fibers being rationally connected, we need the theorem A. Okay. And another thing is we don't know whether the smoothness of Y can be dropped. Okay. So the smoothness of Y is to make sure that this F is locally constant by Matsumura Wang and Campana Cao Matsumura, okay, by the two joint works. Okay, and this work they deal with the KLT pair case, and this paper they deal with the smooth case with boundary. However, actually, if we have already assumed the local constancy of F, in other words, if we start from a locally constant fibration from a normal projective variety X, then we can remove the smoothness of Y. Okay, so actually, if we just change the first sentence to the locally constant fibration from a normal projective variety X to a normal projective variety Y, then the remaining conclusions still hold. Okay, so the smoothness is just to make sure this fibration F is locally constant. Okay, so finally, this is our last main result. Okay, so our third result is to answer the log version of Campana-Peter-Nels conjecture affirmatively in dimension 3. Okay, so if X delta is a projective KLT pair with the anti-log canonical divisor being strict F, and if this is dimension 3 case, then our minus K plus delta is ample. Okay. So recall that the Uehara in 2000 he took the first glance on the singular case when X is a threefold with only canonical singularities and the zero boundary, okay, vanishing boundary. There's no boundary in the first glance. Okay, the key point is to show that this theorem C is to show that this minus K plus delta is numerically equivalent to an effective divisor. Okay, so so this means that if we can find a non-zero effective divisor numerically equivalent to this anti-log canonical divisor, then together with the strict F-ness, we can show that this minus K plus delta is ample. So this is a proposition. Okay, so let X delta be a projective KLT threefold pair, and this LX be a strict F Q divisor on X. And suppose that this strict F divisor LX is numerically equivalent to a non-zero effective divisor, then this KX plus delta plus TLX is ample for sufficiently large T. This proposition has some other versions due to in our different situations of the proofs. and we will see some other versions tomorrow. Okay, but here we can see in our case, if we can show this minus k plus delta is strict F, which is just this Lx, then this is ample. Okay. The idea to prove this proposition is to show that is just to write this non-zero effective divisor as some components, okay, as some Fi. Then by using the adjunction, we reduce to the subvarieties, to the surface case. And then in the surface case, everything has already been known. Okay. Okay, so now in what follows, I will give some ideas for the proofs of our three theorems. Okay. So the first, so for the theorem A, let's recall we show the rational connectedness of this x delta with minus k plus delta being strict F. Okay. So we need this very technical theorem. Okay. So I call it the section of the MRC fibration. Okay. So we start from this x delta, which is a projective KOT pair with the anti-log canonical divisor minus k plus delta being Nef, okay, being Nef. Then up to replacing x with a quasi-tau cover, the MRC fibration, the holomorphic MRC fibration as proved in the Matsumura-Wang, okay, we can show it is a locally constant fibration admitting a section sigma, such that this sigma, the pullback, this kx plus delta is numerically trivial. Okay, so note that this is locally constant fibration, which is already proved in Matsumura-Wang. And what we did is to show this F admits a section from Y to X, such that the restriction of this kx plus delta on this section is numerically trivial. Okay. So note that this theorem will imply our theorem A because we just take the locally constant MRC fibration after replacing X by a quasi-tau cover. So note that if this is trivial, then if this is Nef minus k plus delta is Nef, then its quasi-tau cover is still Nef. The minus k plus delta is still Nef. And suppose the contrary that this X is not rationally connected, then the downstairs dimension Y, the dimension will be positive. Okay. By the above theorem, we can show this F admits a section sigma such that the sigma pullback kx plus delta is numerically trivial. Okay. Then we pick a curve C in the Y. And by the projection formula, we see that this is 0 when you do the intersection with this C. And then it should be equal to minus kx plus delta times sigma push forward C. Okay, note that this is still a curve. However, this is strict F by our assumption in the theorem A. So this is positive. Then we get a contradiction. Okay, so the most important thing to show theorem A is to show our technical theorem, but I will skip the proof here. The proof, we need to use the, we need to study the periodic points of the fundamental group of Y on the fibers. Okay. So this is the proof, the idea for the proof of theorem.
Sorry, wait a moment. Sorry, I'm a bit okay here. So how do you get a contradiction? Where is the contradiction? So
the contradiction, the left-hand side, because we find the section, this sigma, such that the kx plus delta restriction on this section is numerically trivial, right? So this is 0.
So you mean what? You mean Y cannot be? Must be a point, right? Okay.
Yeah. In this case, Y must be a point. Okay, so it is rationally connected.
Okay. I see.
Okay. So this is the idea for the proof of theorem A. And notice that this section of the MRC fibration, this theorem holds for the condition we only require this is Nef. Okay, we don't need this is strict Nef. Okay, so this is theorem A. Okay, theorem B should be bit more technical, and I will try to simplify the proof. Okay, so we start from a fibration x delta to y of a projective KLT pair x delta onto a smooth projective manifold y, such that this minus k over y, x over y plus delta is nef. Okay, so similarly, we only first require this this relative anti-canonical divisor is nef rather than strictly nef. Okay. Then we still need to show a technical lemma, okay, but I will just put it here, okay, without any proofs. So we denote by T the Zariski closure of the union of curves in X, such that they have the zero intersection with minus k over X over Y plus delta. So in other words, we just find all the curves such that it has zero intersection with the relative anti-log canonical divisor. Okay. In particular, in our strict nef case, this T is empty. Okay. So if T does not dominant Y, if this T does not dominant Y, then we can show that this Y is of general type, and there exists a linear representation chi from the fundamental group whose image is not virtually solvable. So virtually solvable means after replacing this group by a finite index subgroup, okay, it is solvable. Okay, so maybe we will return back to this technical lemma when I prove this theorem B. Okay, and another lemma we also use, this is proved in the joint work by Jie Liu, Wen Haoo, and Xiaokui Yang in 2020. Okay, so they show they give the relationships between the fundamental group and the degeneracy of entire curves. Okay, so with we consider a irreducible projective variety Y, and if there exists a representation rho, okay, such that its image is not virtually solvable. Okay, just this conclusion of our technical lemma 1. Okay, so if there exists a representation such that the image is not virtually solvable, then every holomorphic map is degenerate. Every holomorphic map is degenerate. In other words, the image is not Zariski dense in Y. Okay, the image is not Zariski dense in Y. Okay, so I will return back to these two lemmas later on. Okay, another thing I have just mentioned in the beginning when stating the theorem B. Okay, so with the assumption above, if we consider a general fiber F of the fibration F, then this F is indeed a locally constant fibration with respect to the pair X delta. Okay, so this means that if we start from this fibration onto a smooth projective manifold Y, such that the relative anti-canonical divisor is nef, then this F is locally constant. Okay, so this is essentially proved in Campana, Cao, Matsumura, and Matsumura Wang. So now we prove our theorem B. So recall that what our theorem B states. So our theorem B says that if the relative anti-canonical divisor is strict nef, then this F is locally constant and the general fiber is rationally connected, and the downstairs Y is canonically polarized hyperbolic. Okay. So by theorem star, we are now left to show Y is hyperbolic and KY is ample, because the general fiber being rationally connected is also proved in theorem A. Okay. Okay, now by lemma 1, we know this KY is big. Okay, because you can see, because in this case our T is empty, so Y is of general type. Okay. So by lemma 1, KY is big. So therefore, to show ky is ample, we only need to show y does not contain any rational curves. Because you can see if ky is big, but not nef, then by the Kohn theorem, y should contain some rational curves. If ky is nef and big, then the non-locals of this ky, of this nef and big divisor is uniruled. Okay, and alternatively, by using the rigidity lemma, we can also show the non-ample locals, of the nef and big divisor is uniruled, contain some rational curves. Okay, so to show ky is ample, we only need to show y does not contain any rational curves. So to show y does not contain any rational curves, we only need to show y is hyperbolic. So actually, these two conditions, hyperbolicity implies the ampleness of this ky. So we only need to show y is hyperbolic. So we let this h be an entire curve, okay, from C to y, okay, and then we denote by the denote by z the closure, the Zariski closure of the image HC, okay, which is a. So suppose the contrary is that this y is not hyperbolic. In other words, we can find a non-constant map H. Then this dimension z is positive. Okay, so this z is positive. Then we can see this HC is not degenerate in Z. So recall that this is degenerate in Z if the closure is not Zariski dense. However, by definition, we can see this HC is not degenerate in Z. Okay. And now we let this Z prime to Z be the normalization, and this F prime be the induced locally constant vibration. Sorry, I forgot to mention a property that the locally constant vibration is stable under the base change. Okay. So we get the induced locally constant vibration from X prime to Z prime. Okay. So now by lemma 1, there exists a representation pi1 Z prime whose image is not virtually solvable because our T is empty. Okay, you can see because our T is empty. Okay, and but here we need to consider the case minus k x prime over z prime. Okay, plus delta prime. Okay. Okay, so so in this case, there exists a representation whose image is not virtually solvable. On the other hand, the holomorphic map H can be lifted to this H prime from C to Z prime by the universal property of the normalization. Okay, so we get the Zariski closure of this H prime C is Z prime by the commutative diagram. However, this contradicting our lemma 2 because according to our lemma 2, every holomorphic map from C to Z is degenerate. In other words, every the image is not Zariski dense, but according to our definition, this H prime C, the closure is just the Z prime. Okay, then we get a contradiction. So in this case, the key point is to show our technical lemma 1 in this case, and the proof needs some Shaff-Rich maps and to show this Y is general type. And there is also we also need some group theory to show the image whose image is not virtually solvable. Okay. So then we apply a previous lemma by Liu O Yang. And finally, we can show our theorem B. Okay, now we prove our theorem C. Okay, so theorem C is not easy. Is not hard to prove. Okay, actually. So we recall a theorem by Jing Junhan and Wenfei Liu in 2020. Okay, so they show that if X delta plus MX is a three-dimensional projective generalized KOT pair, here this generalized pair means this is a there are many models, okay, and then this MX may be the push down of some NEF divisors from higher models, okay. such that this mx is an R-linear combination of Neff-Cartier birational divisors. Okay. And suppose that this kx plus delta plus mx is pseudo-effective, but kx plus mx is not pseudo-effective. Then this kx plus delta plus mx is numerically equivalent to an effective R divisor. Okay, so this delta, the existence of this delta is very important. Okay, because the existence of this delta can have some properties, and then once you can show this is pseudo-effective and this is not pseudo-effective, then we have the sum kx plus delta plus mx is numerically equivalent to an effective divisor. And together with our previous proposition, okay, so if it is numerically equivalent to an effective R divisor, then it is ample. Okay. So now we start from a KLT threefold pair X delta. So recall that our theorem C confirms that if minus K plus delta is strict Neff, then minus K plus delta is ample in dimension 3. Okay. So we start from a KLT threefold pair X delta with strict Neff minus K plus delta. And we take a Q factorial terminalization Y gamma to the X delta, such that this Y gamma is a Q factorial terminal pair. Okay. And if gamma is not equal to 0, by some calculation, we can show that this kx, we can show that this minus ky plus gamma is numerically effective by the theorem of Han and Liu. Okay, we need to do some calculations. Okay, just let this mx be a suitable multiple of this ky plus gamma. Okay, so if gamma is non-zero, then we are done by the above two results. And if gamma is equal to 0, then this delta is also equal to 0. And in this case, we reduce to the case when X has only canonical singularities. Okay, when X has only canonical. So in this case, X itself has only canonical singularities, and the boundary delta is 0. So in this case, which we can just apply Uehara's result. Okay. And of course, sorry.
Why you say X has only canonical singularities?
I think because by calculating the discrepancy, in this case, ky is just the pullback of kx, right?
Or you simply reduce to y0, y has terminal singularity, so you consider on y or not? Where do you use the y here? Use the terminal model here.
Yeah, you are right. If gamma is equal to 0, then no. In this case, minus ky is almost a strict Neff. So maybe we still need the strict Neffness. So we need this X. Here the terminal model is to let me see. Oh, yeah. Actually, I see. I think this proposition, we should need the Q factorial. Maybe no, let me see.
I think if you say your gamma is non-zero, you apply the above two results. But Han-Liu theorem will only assume that X is the KLT, right? So no need to use Y here, right? Gamma non-zero.
Yeah.
Where did you? Where did you?
Yeah, actually, for this about this proposition, we need the Yeah, in the, on this proposition, maybe we need the Q factorial property, but this is the general form. I'm not sure, but this is, let me see. Yeah. I think you are right. I think you are right. Here maybe we don't need to take the Q factorial terminalization. Yeah, because actually initially we prove this proposition by assuming this x is Q factorial, but later on actually I'm now able to show the non-Q factorial case. So actually, by using the non-Q factorialness, the proposition, we can drop the Q factorial terminalization. Yeah.
Okay, so you use the minimum model program here or not? Did you in this proposition?
This proposition, we don't need to use the minimum model program. We just reduce to the subvarieties.
Okay, so you also don't need the Q factorial terminalization. Do you? Do you need this?
In this proposition, for the proof, we need to take the Q factorial.
Q factorial
terminalization. Yeah. Because otherwise, the junction may not have some problems, I think. Okay, yeah, for the proof of this proposition, we need to take the Q factorialness. Yeah, but in the proof of our theorem C, yeah, now we can drop the Q factorial terminalization. Yeah, you are right.
I see.
Thank you very much. Okay, so this is the idea for the proof of theorem C. Yeah, so there is a process. Yeah, initially I can only show the Q factorial case. Then later on we can drop the. We may study this. We may discuss this proposition and some other versions tomorrow. Okay. Tomorrow. Okay. So finally, I will ask some open questions. So first is still about the previous problem about the strictness. So in the relative case in our theorem B, we want to know if the downstairs is not smooth, but we assume this minus k over x plus y is strict enough, then will such f be locally constant? Okay, because we know that in our case, if the downstairs y is smooth, then the relative anti-canonical divisor being nef will imply this f is locally constant. But in general, we want to give a more stronger condition that this relative anti-canonical divisor is strict nef. Then we want to know whether the local constancy can also be deduced. Okay. So, but note that this question has a negative answer if minus k over y plus delta is only nef. Okay. Because we just consider the terminalization x delta to y of a projective KLT variety y. Okay, then in this case, the relative anti-log canonical divisor is relatively trivial. Okay, it's relatively trivial, but clearly this f is not locally constant. Okay, so we want to know whether the strict nefness will help to deduce the local constancy. Okay. So in general, we expect the strict nefness could restrict and control the behavior of f. And another question is about the positive characteristics. So if we start from a strongly F-regular pair or a more generally sharply F-pure pair with strict nef minus k plus delta, and we want to know whether this X is rationally chain connected and whether this minus k plus delta is ample. According to my calculation, the surface case is not very hard. But from threefolds, we also need to develop some new tools to study this question. Okay. So I think I will stop here today. Okay, thank you.
Okay, thank you very much. Okay, very nice talk. So any question? Okay. I guess you turn to the previous page. The question one, I have some idea. Is your strict nef this relative version of strict nef preserved by the base change of y? Have you ever tried?
But in this case, we need to require this y is q Gorenstein, if I remember.
For example, you just
correctly.
take the resolution of y. Is it okay? Is
Actually we can show if this y is q Gorenstein, then the G pullback of this I mean the induced morphism maybe you just take the y prime to y,
Yeah.
and then you have the base change. Then we denote by this base change by G. And then we can show this G pullback, this kx over y plus delta is just the upstairs the information, the kx prime over y prime plus delta prime. But we need the downstairs y being q Gorenstein, I think.
Okay.
Yeah.
Okay.
Okay, you can continue. If we can show the upstairs is still strict left, then what do you want to say?
Yeah, you at least you have some control on x tilde, right? Or
Yeah.
You can say y tilde is now y tilde is smooth, so it's
yeah.
hyperbolic, right? So it is general type. So y is also general type. Right? That's all.
Right. Yeah.
But I also feel very strange in surface case. When x is a surface, I guess you don't have such an example of this strictly naive, relative strictly naive condition, right? For example, if
yeah, actually we don't have any examples on the on this case. I mean
this condition is very strong, and the example is very difficult to find. So you at least you can only find this in dimension 3. X is
Yeah, actually we can only find some examples on the NEF case. The string NEF case seems to be very strong. Yeah. But the locally constant condition is also very strong. Yeah.
What do you mean by locally constant? Oh, you are not locally fabric. Local. What do you mean by?
Yeah, I mean in this case,
what's the locally constant?
I mean in this case, the local constancy of this f can be deduced from the smoothness of y and the naifness of this minus k plus.
What's the definition for locally constant?
Locally constant means the every fiber there are 3 conditions, so every fiber is are isomorphic, and the universal cover of this y after the base change, it splits into the
I see.
y prime times, yeah. So
in which kind of base change? Eta base change or
I think it's just the usual base change. No need a eta base change, I think.
And okay, you can do any base change, you mean?
Yeah, any base change.
Any base change.
You mean what do you mean the base? But I mean the base change is take the universal cover.
Universal cover. Okay.
Yeah, this is the universal. I mean the base change. Any base change means the local constancy is stable.
And your splitting is in the analytic sense, not in the algebraic.
Yeah. It is just only analytical case, not algebraic sense.
Okay, so in calculus P, this is very difficult.
Yeah. In calculus P, there are they seems to already assume this minus ky being semi-ample. Then they can have some results, but for the non-semi-ample, just if we only assume it is NEF, then it seems to be very.
I forgot. If it is a locally constant vibration, then you have a section, right? You said. In which lemma you said this f has a section?
Yeah. This f has a section in over. In complex numbers, yeah.
No need base change, simply for f. Do you need any base change for y to find a section, or simply work on this?
Yeah, we need to replace this y by some further base change, 一套 base change, I think.
Then you can find a section.
Yeah. Because this something related to the flat subbundle and the fixed point. Because we can only consider the periodic points, but the periodic points, the fixed points is in one-to-one correspondence with the section. So these periodic points, we need to replace this y by some 一套 cover, I think.
Okay.
Yeah.
I guess question 2 may not be doable, but question 1 is okay.
Yeah. Actually, question 2, the surface case seems have the same strategy, but the threefold is very, very hard. I'm still
surface is not interesting, I think.
Yeah. So, but surfaces seems almost trivial, but yeah.
I remember you mentioned about a lemma, but you had too many lemmas, so I cannot remember. You have a lemma mentioned that you can use a junction to say something, right? Can you move to the previous slides? Maybe.
You mean this lemma, or
you use this lemma? You use this you use a junction here, right?
Yeah, here I need to use a junction to reduce to the surface case for the
adjunct to the effective divisor, components of the effective divisor.
Yeah, components of this effective divisor. Yeah.
And why you need to assume this is a threefold?
Because when you reduce to the surface case, then you can apply the Cyrano's conjecture. Because the strict divisor restriction, yeah, then you use the surface case. In general.
Okay, so in threefold, the characterization of strict left divisor is still unknown, right?
Yeah, the Cyrano's conjecture is still widely open in threefold case. We only have some results on the Campana-Peter-Nels conjecture. Yeah.
Okay, because you have the assumption, but on fourfold, when you do a junction, you don't have such assumption that this is null. If x is if x is 4 dimension and you do the adjunction on the components is the threefold, and
then you need to show this. For example, this component is D. Then you need to show KD plus TLX restriction to D is ample. But this is the log version on the Cyrano's conjecture rather than Campana-Peter-Nels conjecture. Because after you apply the junction, you get the canonical divisor K. And so there is a turbulence of the canonical divisor K. So this is not the pure version of the Campana-Peter-Nels conjecture. Yeah. So this is the reason why Haidong Liu haven't got a full version in dimension 4 of the Campana-Peter-Nels conjecture.
Okay. Okay, I see. Okay, thank you. Okay, any other question? Okay, if no, let us thank the speaker. Okay, thank you. Let's
okay, thank you.
Then see you tomorrow. Okay.
See you tomorrow. Okay. See you.
Okay， 所以你基本上这个都讲完了啊，是吗？还是说哪里我把这个取消？